Hello everyone, I am Dr. V. Radhika Devi, Professor in Physics and Dean of Science and Humanities Department at MLR Institute of Technology. In this video, today we are going to discuss about the introduction to quantum mechanics. Let us embark on a fascinating journey of quantum mechanics that challenges our classical understanding of the universe and reveals a reality that is far complex and yet very much intriguing. Classical physics deals with the macroscopic scale of the particles, whereas quantum physics deals at the macroscopic or let us say nanoscopic scale, which means atoms, the particles that are present inside the atom, like electrons, protons, and how they are about to move. At first, it may appear that whatever facts that the classical physics was dealing and how the quantum mechanics has counteracted, it seems to be counterintuitive. For example, the wave particle duality that was presented by de Broglie, which talks about the particle being acting as a wave. The other very important concept is the quantum superposition. This quantum superposition is again a thing which challenges the concepts of classical physics. And the quantum entanglement. This is again a new concept which has completely changed the way that technology is running today. Quantum mechanics not only redefines the understanding of the universe, but also it lays the foundation to the modern technologies, like starting from semiconductors, which we use in our computers, to smartphones, which we use day-to-day life. Not only these, but quantum batteries that never run out. We talk about quantum computing, which completely depends on the laws of quantum physics. The quantum cryptography, the one which we talk about the currency, how do we secure things, all the things like quantum battery, quantum computing, quantum cryptography, everything is dependent on the principles of quantum mechanics. At its core, quantum mechanics deals with the probability and uncertainty, which are the fundamental aspects of the quantum world. Whereas, as per classical physics, there is no uncertainty. Quantum laws are governed by Heisenberg's uncertainty principle and are embarked in the Schrodinger's equation, which we'll be checking in the next videos. So, when we look at quantum mechanics, where has it born? So, looking at the birthplace of quantum mechanics, it is the black body and its radiation. As you can see, a black body is the one which emits all the radiations once it gets heated up. Or for that matter, a black body is the one which takes up all the radiations that are incident on it. It absorbs all the radiations. And it starts emitting all the radiations, which is a function of the temperature of the body. So, Planck was the person who explained the observations that were done under the black body radiation. So, let us look at the spectrum and what the spectrum has defined. So, the key observations of this particular spectrum, where you can see that an experiment was conducted with respect to the wavelength that was emitted out by the black body and the intensity of radiations that were emitted out. It is observed that a black body spectrum depends only on the temperature but not on the material with which the body is made up of. That is a very interesting fact. As the temperature of the object is increasing, it is noted that black body radiation will also increase. As the graph you can see, at 3000 degree Kelvin, how much is the peak, and as the temperature has increased to 4000 degree Kelvin, the peak started increasing. This is again a very interesting point to be noted. So, as the temperature of an object is increasing, black body radiation also increases. The peak wavelength of this black body spectrum becomes shorter as the object's temperature rises. As you can see from these points, yes, these are the points where it is very clear that the peak wavelength is becoming shorter and shorter, as you can see towards the shorter wavelengths. Also, the black body radiation curve for different temperatures will peak at different wavelengths that are inversely proportional to the temperature. Yes, at 3000 degree Kelvin, you can see this is what the peak is, and at 6000 degree Kelvin, this is what the peak is all about. So, these were the observations that were not tackled by classical physics. So, there was some kind of understanding that a separate physics is needed, and that's where Planck has given some sort of understanding about what happens inside a black body. So that led to the foundation of Planck's black body radiation law. This particular radiation law is a mathematical relationship which was formulated by the German physicist Max Planck in order to explain the spectral energy distribution which was emitted by the black body. Planck has assumed that the source of radiation that is coming out from the black body are the atoms which are in a state of oscillation, and that the vibrational energy, as you can see, the vibrational energy of each oscillator may have any series of discrete values but never any value between 0 and infinity. And we can understand when an oscillator changes from one state having energy E1 to another state, let us say a lower energy state E2, the discrete amount of energy, which is the difference between the two energy states, is given out in the form of a radiation, and that is what we call it as the quantum radiation. Again, this quantum radiation is equal to the product of the frequency of the radiation, and there is a constant that is given by Planck, and that is what is called as the Planck's constant. As you can understand, Planck's constant, H is equal to 6.63 into 10 to the power of minus 34 joules second. With this understanding that the energy difference that is coming out in the form of a radiation is proportional to the product of frequency of radiation and the Planck's constant, further it was emphasized that this particular intensity that is emitted out by the black body radiation is as a function of wavelength, you can just see, is equal to 8 pi hc by lambda to the power of 5, which means the energy emitted is inversely proportional to the fifth power of the lambda. And also you can see it is e power hc by lambda kt, where k again stands for the Boltzmann constant, which is equal to k is equal to 1.38 into 10 to the power of minus 23 per Kelvin. Now, if we try to understand, this particular law is different from what classical mechanics says. So that's all for this video, and in the next video we will be looking at what de Broglie hypothesis is and how the wave particle duality can be confined.